Today I will discuss temperature effects on one-dimensional problems. The stresses induced by temperature changes in an isotropic linearly elastic materials will be considered. That is, the thermal stress problem will be considered. The stresses induced by temperature changes in an isotropic linearly elastic material will be considered. That is, the thermal stress problem will be considered if the distribution of the change in temperature delta T of x is known. Then the strain due to the temperature change can be treated as initial strain epsilon naught is given by epsilon naught is equal to alpha into delta T. If the distribution of change in temperature delta T of x is known, then the strain due to the temperature change can be treated as an initial strain epsilon naught is given by epsilon naught is equal to alpha into delta T, where alpha is the coefficient of thermal expansion. A positive delta T implies a rise in temperature. The stress strain law in the presence of epsilon naught. The stress strain relation sigma is equal to E into epsilon minus epsilon naught is equation 1. Next, the strain energy for unit volume U naught is equal to shaded area in the figure. So this one is shaded area on this figure. Epsilon and sigma and epsilon naught. The strain energy for unit volume U naught is equal to shaded area of in this figure. U naught is equal to half into sigma epsilon minus epsilon naught. This is equation 2. From 1 and 2 equations, U naught is equal to half into epsilon minus epsilon naught into E into epsilon minus epsilon naught 3. The total strain energy used in the structure is obtained by integrating U naught the volume of the structure. U is equal to half into integral epsilon minus epsilon naught whole power transpose E epsilon minus epsilon naught A into dx from equation 4. For a structure model using one-dimensional linear elements, U is equal to sigma of half into A into LE by 2 epsilon minus epsilon into T E epsilon minus epsilon into d psi, where dx is equal to LE by 2 into d psi. Nothing that E epsilon is equal to BQ. Substitute B value, epsilon value B into Q. Therefore, U is equal to epsilon E half into Q transpose E A L by 2 integral minus 1 to 1 B transpose B d psi into Q minus epsilon Q transpose E A L by 2 epsilon minus integral minus 1 to 1 B transpose into d psi plus epsilon half into E A L E by 2 epsilon whole square. Therefore, the first term is element stiffness matrix derived in the previous sections. K is equal to EA by L 1 minus 1 minus 1. And next, d pi by dx d pi by dou theta is equal to 0 or d pi by dq is equal to 0. We take second term E A L E by 2 E integral minus 1 to 1 B transpose into d psi, where B is equal to 1 by x2 minus x1 minus 1 1 and epsilon naught is equal to alpha into delta T, where theta is equal to EA by L alpha delta T x2 minus x1 minus 1 and 1. Delta T is average change in temperature within the element. Therefore, F is equal to sigma of E Fe Te plus theta E plus P. The stress sigma is equal to E into epsilon minus epsilon naught, where epsilon is equal to BQ and epsilon naught is equal to alpha into delta T. EBQ minus E alpha delta T. E by x2 minus x1 minus 1 1 into Q minus E alpha delta T. The temperature affects the stresses